Okay, so now we're just going to do some numbers for the proportions of singletons that we expect for samples of different size. So in the aside, the short video I just did, I pointed out that there's something wrong with this expression when n is 2. So we'll start with n equals 3. So for n equals 3, we can just make a chart here, and then this would be expected number of singletons. So expected number of singletons, expected number of SNPs, and proportion of singletons. The expected proportion of singletons. Okay, so let's make our lives easier, and we're just going to take out a 2nu term. So these will be all times 2nu. Okay, so then for n equals 3, then this is just 3 divided by 2. Actually, let's just make it nu. 3 divided by 2 times 2. So this would be 3nu. And the expected number of SNPs would be the sum from 1 to 2. So that would be, so when I is 1, this is 1 over 2. And when I is 2, this is 1 over 1. Okay, so we get 1 over 2 plus 1 over 1. So we get 3 halves times 2 times nu, which is equal to 3 halves times 2, which is 3. Okay, so expected number of singletons is 3, expected number of SNPs is 3. So we get 3 over 3 is equal to 1. So does this make sense? Well, if we think about a 3 individual tree, any mutation that occurs, mutations occur on this branch, give SNPs, give singletons. Mutations that occur on this branch give singletons. Mutations that occur on this branch give singletons. So we expect everything to be a singleton. Either these two are different from this one, or these two are different from this one, or these two are different from this one. So that makes sense. For a 3 taxon tree, for a sample of size 3, we expect all of our mutations to be SNPs. All of our SNPs to be singletons. Okay, what about for 4? So now our expectation is to be 4 divided by 3 times 2, or 8/3. Get that right? 4 divided by, yep. And then this we expect it to be 1/3 plus 1/2 plus 1 over 1 times 2. So that's equal to 3 halves, 9626. Okay, this is equal to 26 plus 36 plus 66 is equal to 11/6 times 2, 11/3. And so our proportion then is 8/3 over 11/3, or 8/11. And so that kind of makes sense, because if we think about a 4 taxon tree, we have a lot of branches where mutations give singletons, and we only have this one where they don't. All right, let's just do one more. Okay, so for n equals 5, then we have 5 divided by 4 times 2 is 10. So our expected number of singletons is 10 times nu. Sorry, our expected number of SNPs. Our expected number of singletons is 10 times nu. Did I get that wrong? I got that wrong. Sorry about that. Our expected number of singletons is 5 divided by 4 times 2, which is 5 halves. Okay, how about this one here? Well, again, we have 1/4 plus 1/3 plus 1/2 plus 1 times 2. So this is 3 twelfths plus 4 twelfths plus 6 twelfths plus 12 twelfths is 23, 25 twelfths. Times 2 is 25 sixths. And so when we divide this by that, we get 3 fifths. And I think that's about as far as I can take it. So this gives a sense, though, of, from all this math, that we get these very simple proportions of singletons that are expected. And so that would mean then that if in real data, we could take our expected fraction of singletons and compare it to our observed fraction of singletons, and basically ask if there are more singletons than we'd expect. Now, yeah, and so I'll just say let's spend 1 minute on why we might care. So in general, rare mutations can tell us about recent population structure. So for instance, if we have in a population that's expanding, our tree tends to have more recent divergences than we'd expect, right? So it tends to be even more squashed, where we have lots of recent divergences and then these big, deep ones. Under those circumstances, we expect more of these more singleton mutations because the recent coalescences are so close together. Another possibility is that more singletons, more rare mutations can indicate selection against newly occurring variants. And so that would be somewhat context specific, but just to give you a sense of why we might care to compare our observed fraction of singletons to our expected number.